G'day everyone, welcome to Lubrication Experts. Today I'm really excited. I know I say that every week, but in this particular instance, we are talking about polyalkylene glycol. So this is a subject which I think everyone has come across at some point, whether it's talking about it in the context of turbine oils or gear oils or compressor oils. Everyone's had some kind of exposure to PAGs, but everyone's knowledge, I find, is a little bit limited. There are a lot of myths about PAGs. It kind of has this air of mystery because it's different to all the other lubricants. So today I have the expert on PAGs. So I'm introducing Martin Greaves, who spent over 2 decades working with polyalkylene glycols in their function as lubricants. And so really excited to talk to him today and get his insight on everything to do with PAGs. So hopefully all your questions will be answered. So Martin, thank you so much for giving us some time.
Rafe, I'm really delighted to be with you today to talk about PAGs. And I want to say a big thank you for everything that you do with regards to educating me and many other people across the lubricants industry on some of the lubrication challenges that we had. So thank you for that.
Oh, thanks, man. I mean, yeah, I just do this for fun, but hopefully other people learn as much as I do along the way. If we get straight into it, maybe the first and most obvious question to ask is, what are PAGs? So everyone knows them as polyalkylene glycols, but that's kind of like an umbrella term for a whole bunch of different molecules. So could we please maybe just start with, like, what is a PAG and how is it made?
Yeah, sure. So PAGs are polymers and they are an API group 5 base stock. And we manufacture these from 3 key oxides: ethylene oxide, propylene oxide, and butylene oxide. There is a large manufacturing infrastructure in place today for manufacturing ethylene oxide and propylene oxide. And we can produce some downstream derivatives of those 2 oxides, which we call polymers. And in our industry, in lubricants, we call these PAGs, but they're used in many other industries as well, from fuel additives, personal care products. They're used in paints and coatings, and many other applications. In fact, ethylene oxide and propylene oxide derivatives are actually very much in our homes, in some of the cleaning products that we use. Indeed, the seat that I'm sat on now is based on polyurethane foam. But in terms of the EO and PO derivatives, we market those polymers as PAGs in our particular industry. There is a third oxide, 1,2-butylene oxide. That is a niche oxide. There's only a couple of chemical companies worldwide that manufacture butylene oxide. And you can produce a new kind of PAG with butylene oxide that we've called oil-soluble PAGs. And maybe we talked a little bit about those. But if you compare ethylene oxide, propylene oxide, and butylene oxide from a pure chemistry point of view, you have ethylene oxide with 2 carbons, propylene oxide with 3 carbons, and butylene oxide with 4. And that extra carbon in butylene oxide for me is a little diamond. And it can bring some diamond-like performance in lubricants. But maybe some purchasing managers would also say it probably brings diamond-like pricing as well. But perhaps we won't talk about pricing today and the commercial aspects, more so on the technical aspects. So that's essentially how we manufacture PAGs today.
Yeah, really interesting. So I think a lot of people will have heard about like an OSP, which you've already just alluded to as being an oil-soluble PAG, right? What's the difference, right? Because you've already talked about, let's say, the other PAGs, the ethylene and propylene oxide ones, which presumably if we have an oil-soluble PAG, that means that there are also PAGs which are not oil-soluble, which is almost a confusing term because people think of a PAG as being an oil, and yet it's not soluble in oil. So could you please maybe like tease out a little bit for us what all these terms mean and what does it mean to be oil-soluble versus not?
That's a great question, Rafe. So if you look at the lubricants industry today, there are more than 100 different chemical families of PAGs that are used. And trying to get your head around all that is quite difficult. But what the PAG manufacturers have done, they've segmented PAGs into essentially 3 classes. There are the water-soluble PAGs. So these are PAGs manufactured from ethylene oxide and propylene oxide. There are the water-insoluble PAGs. They're manufactured from propylene oxide, but the water insoluble PAGs are not water soluble, nor are they oil soluble. And then there are the oil soluble PAGs, which are truly oil soluble, but not water soluble. So think of those three families of PAGs when we talk about PAGs going forward.
And when you say there's like hundreds of different types, are these hundreds of different types just iterations on using those three different molecules? So you had ethylene, propylene, butylene oxides, but using them in different combinations?
Right. In different combinations. And maybe I can explain that a little bit more. In the manufacturing process, there is an initiator. It's typically an alcohol in our industry. And so what we can do is we can graft onto that alcohol an oxide, and we call those polymer polymers. But we can also produce copolymers as well, typically random copolymers where we have ethylene oxide and propylene oxide in the mixture. But not only random copolymers, we can produce block structures where we have a block of ethylene oxide or a block of propylene oxide, and then a second block of ethylene oxide or propylene oxide. So these randoms, blocks, and indeed reverse blocks, and we can change the alcohol. The alcohol can be an alcohol with just one free OH group, or maybe it's a diol with two or a triol with three. And when we look at all those many different families of polymers, they have different physical properties, they have different tribology properties, and they have different applications depending on the architecture of PAG. And this is why I think some people have a lot of challenges around trying to understand what PAGs are and why they're used in a very diverse range of applications.
Yeah, that's interesting. So we should think of them more as like a family of different molecules or compounds as opposed to being one thing. And I think, from us in the lubrication world, because when we talk about synthetics, typically we're talking about polyalpha olefins, right? And yeah, okay, there's conventional versus metallocene PAOs, but at a chemical level, they don't act that differently, right? It's carbons and hydrogens just kind of organized in different ways. The opportunity with PAGs is to be able to get a lot more variability out of a family of molecules. Is that fair to say?
It is very much so. They're very, very versatile as polymers, and we can design them in many different ways, as I've described. And what I would say, Rafe, from a pure chemistry point of view, if you look back over the last 75 years when PAGs were first introduced, and you draw these structures on paper of the more common PAGs, they're hypothetically linear structures.
Hmm.
What hasn't been done is work around branched and hyper branched structures. And we have these modern tools now to measure friction very, very rapidly. So that all research is ahead of us in the future. And I'm sure we'll see many more different types of PAG families being used to solve some of the challenges that our lubricant industry faces today.
Yeah, really interesting. So maybe the archetypal PAG that has been used in our industry in the past is one that I'd say operators are slightly scared of. You already mentioned price, but we're not going to talk about that because that is one thing that they're scared of. But that's true of all the synthetics, right? So one thing that everyone gets a bit scared of is the compatibility issue, right? Whether it's compatibility with other oils, paints, seal materials, and things like that. Could you please maybe expand on why is it that historically PAGs have had really poor compatibility with other components? And then are there ways to get around that?
Well, sure. I think the starting point, Rafe, and all that is that PAGs can be used in many different types of equipment and have been used, as I said, for the last 75 years. So none of those problems you mentioned are insurmountable. But those three things are very important. If you're transitioning your equipment from a hydrocarbon oil to a PAG, you need to take care of the flushing procedures for the reasons you mentioned, that there is some incompatibility there. So that's the first thing. Regarding paints and coatings, there are certain paints where PAGs are compatible. The epoxy and the phenolic epoxy type paints are fine. The alkyd and vinyl paints have some challenges, so you've got to be a little bit careful with regards to the paints. And then on the elastomer side, in fact, most elastomers are fairly compatible with PAGs, and the fluorine-based elastomers like Viton, very compatible. The NBR ones, the Booner N, the cheaper elastomers, uh, they're compatible when the nitrile content is very high in the Booner N, but the low nitrile containing seals tend to have some issues with compatibility. You need to avoid seals like polyurethane seals because the chemistry of PAGs is very similar to the chemistry of polyurethanes. But as I say, by and large, those three aspects are not insurmountable from an equipment point of view. But I fully understand why the end users are sometimes a little bit nervous about using PAGs when they've had many years of experience using mineral oils.
So when I try and explain that incompatibility or compatibility to my customers that are looking at using a PAG, maybe if I can try this explanation on and see if I've been giving them the wrong explanation for the last 10 years. So the way that I described it was that most of the traditional oils that we're used to, whether it's the mineral, group 2-ish style in industrial lubricants, or even the synthetic PAOs, they're all basically non-polar. And so everything that we put in the systems are designed to be compatible with virtually non-polar fluids. PAG, which, I'll have to try and draw the structure on screen for people, is a little bit more polar, and, the water-soluble ones can form hydrogen bonds with water and things like that. So that kind of molecular structure is at odds with everything that we designed our systems for, and that polarity is what runs you into trouble with some of the seal materials and things. Now, how far off the mark is that explanation?
I think it's a pretty fair explanation. The fact that PAGs are very polar. So from a chemistry point of view, again, every third atom along the alkoxide fraction of the polymer is an oxygen atom. But that oxygen atom brings tremendous benefits in terms of some lubricant applications, in terms of friction control, in terms of viscosity, temperature, behavior, um, many, many different aspects in terms of equipment cleanliness and so on and so forth. So I think your explanation is very accurate and care just needs to be taken in transitioning to a PAG. But once customers have or end users have transitioned to a PAG, in my experience, they rarely go back to a hydrocarbon oil. So that's the good news.
Yeah. Well, that's a great segue into what I wanted to talk to you about next, which is all the benefits that come along with using PAG style lubricants. Because in like you said, in my experience, there's a lot. But it might be helpful if we can explain maybe how some of these benefits come about. Because I think a lot of the time, again, because this is like the mystery fluid, there's a lot of hand waving that goes on, and people just say, it has better lubricity because PAGs, without actually explaining how that better lubricity comes about. So maybe we can start with that one, which is you always hear about this better lubricity and friction control and things like that. So what about a PAG gives you that property?
Yeah, okay. So it really comes down to surface activity, but also in terms of the flexibility of the polymers. And let me try and answer that question, Rafe, in a very straightforward way. There are certain friction testing apparatus, the mini traction machine is a very, very good one, that can measure traction values of base oils very easily. And if we take gear applications as an example, we can design the mini traction machine with just steel ball rotating on a steel disc to mimic some of the conditions that we might find in a gear system. So high contact pressures, subsliding, high temperatures, and so on. What I've done over the years is I've looked at many group 1 to group 5 base oils and made some measurements using the mini traction machine. And a lot of that data is published data. What you find is that with certain PAGs, and I stress the word certain PAGs, they have tremendously low traction values. And it's mainly the ethylene oxide, propylene oxide copolymers. Their traction values are much, much lower than hydrocarbon oils, so the group 1 to group 4 hydrocarbon oils. It means that if you're designing a fluid that needs to be energy efficient, your starting point could be a PAG. Now, having said that, there are some PAGs that actually have much higher traction values. So the water insoluble type, the PO homopolymers, their traction values tend to be very similar to hydrocarbon oils. Why? Because the polymer structure is not as flexible as with an EO-PO copolymer. So it's all about flexibility. The oxygens do bring some flexibility within the structure. And if I can finally add, perhaps a question that you may ask is, so where do the OSPs fall on that traction curve? And the OSPs would fall somewhere in between the EO-PO copolymers and the PO homopolymers. So I hope that gives you some kind of sense as to why these materials have some interesting traction behavior. And we just have one final point on that, and that is the oil-soluble PAGs have been designed to try and upgrade hydrocarbon oils. And one thing about the oil-soluble PAGs is that they are also oxygen-rich polymers. Those oxygen-rich polymers are surface active. And so you can include those oxygen-rich polymers into hydrocarbon oils to help with friction control, perhaps under boundary conditions or EHD conditions.
Okay, interesting. So they can almost be used kind of like EP additives, almost.
Yeah, I wouldn't describe them as EP additives, but they certainly have some anti-wear characteristics. Again, the rich nature of the oxygen-rich nature of the polymers leads them to have excellent anti-wear characteristics. You can measure that on the classical all-bore wear test.
So in my envisioning of it, what you've described is kind of a long, almost linear polymer that has a good degree of flexibility to it. And so presumably, we'll probably get to this, that also gives you a really good viscosity index. Now, in the traditional hydrocarbon world, we would think of a molecule like that, what I've just described is a straight chain paraffin, right? And the straight chain paraffins, fantastic viscosity index, you get that same kind of really good flexibility and all that. And you pay for that with pour point, because then they all turn into wax crystals. So I guess the obvious question is, do PAGs suffer from the same issue, or is the nature of the fact that they're not quite exactly straight? You've got, for want of a better word, lots of triangles connected together. I know that's a very poor definition, but does that help you with the pour point control?
Well, during the polymerization process, you have these short branches off the polymer backbone, typically methyl branches or ethyl branches. And because of that, that helps with the low temperature properties. So you'll find that PAGs have very low pull points, for example. The classical EO-PO copolymers, typical pull points, minus 30 degrees C. The oil-soluble PAGs will go down to much lower pull points because of the greater degree of branching, coming off the polymer backbone.
Okay, awesome. So another thing that you brought out was the fact that it contains a lot of oxygen, this molecule. And in my idiot's guide to PAGs, the way that I've always described the oxidation stability is, well, you can't add oxygen to this molecule because it's already got a lot of oxygen in it. So that's why it's so oxidatively stable. Now, I'm sure that the specialist chemists who understand PAGs are like screaming at their either their phone if they're listening to this on a podcast or their TV or whatever. But could you please, I mean, they have a reputation for really good oxidation stability. So could you please help explain why that's the case?
Yeah, so they are fairly good in terms of oxidation stability. I think there are some other base fluids that are more stable from an oxidation stability point of view. But you can use PAGs on a continuous basis in a piece of gears or compressors at temperatures, say, for example, up to 120 degrees C, when they're protected with a good antioxidant package. And I'd always recommend the aminic antioxidants. The alkylated diphenylamines are very good at those types of temperatures. When you go to higher temperatures, Rafe, you start to run into some problems, particularly when you go north of 150 degrees C. And that's where you need to have some very, very good stability of the lubricant by using, so extremely good antioxidants. A really important point, though, about these types of PAGs is when they degrade. They degrade to smaller oligomers, which in turn degrade to smaller organic molecules like aldehydes, ketones, and acids, and so on. But the point I want to make about that is that those oxidation byproducts are very polar, and those oxidation byproducts are soluble in the parent base oil. And it's one of the reasons why PAGs, when they are in equipment, run very, very clean
Mm.
because of those oxidation byproducts being polar. That is unlike hydrocarbon oils. So hydrocarbon oils, as you described, carbon, hydrogen. When you introduce oxygen through an oxidation process, you have um, materials that are more polar. And because they're more polar, those oxidation byproducts can drop out of that non-polar base oil. And this is why we've had some challenges over the years with things like the group 2 and group 3 hydrocarbon base oils. So it is one of the big advantages of PAGs that I feel is that when they eventually degrade, then we don't see issues with deposits and varnish and so on.
Yeah. Well, so that's an interesting point, which I did want to address during this discussion, was that PAGs are in some cases marketed as being, varnish free, whatever that means. But presumably what they're talking about is that sort of keep clean performance, in that when they do degrade, they don't form the standard kind of polar, well, they do form the standard polar molecules that everyone else does when it oxidizes, but with oil-soluble PAGs, you're able to keep them in solution versus having them played out, and become sludge. The question I did want to ask, though, is um, every base oil kind of has its Achilles heel in terms of breakdown. So, some things turn to sludge, some go to varnish, some have thermal stability problems. Obviously, the esters are well known for having hydrolytic stability problems. So, what's kind of like the PAG's Achilles heel? Like, what is its undoing? I've heard some talk about if you expose it to a strong acid or a strong base, it can sort of unzip the molecule, but you'd be better placed to discuss that.
Yeah, so maybe I can just address the varnish part of your question
Mm.
first of all, because maybe I can share a little story with you here. If you go back to the 1980s, then there were some big issues with rotary screw air compressors and the use of rotary screw air compressors containing hydrocarbons. They were forming a lot of deposits and varnish in those types of compressors. And the industry transitioned many of those types of formulations over to PAGs. PAGs solved the problems of varnish and so on and had a much longer life. And today, PAGs are used in rotary screw air compressors as a preferred type of synthetic lubricant over many other technologies. Then, if you then fast forward from the 1980s into around about the year 2005, I would say, we started to hear some issues with varnish formation in gas turbines. And I know you know a lot about gas turbines, certainly much more than I know. But with regards to varnish formation in those gas turbines, it was because of the degradation of those group 2 and group 3 hydrocarbons that were being used in those types of turbines, causing that varnish to occur. And then what happened was at least one OEM decided to make the transition from a hydrocarbon-based gas turbine over to a PAG-based gas turbine, or having heard the story that had occurred in the 1980s with rotary screw air compressors, which were a smaller type of turbo machinery, of course. That over many, many years, many different gas turbines were then converted over to PAG technology. And I think what we're hearing now are these claims around varnish-free PAG-based lubricants for turbines. Now, back to the second part of your question on what is the Achilles heel, with PAGs, those three things that we mentioned before around mineral oil compatibility, paint compatibility, elastomer compatibility are three important things. There's one other thing that I think end users perhaps need to be aware of, and that is When you're condition monitoring PAGs, it's very important to track the acid value of the PAG. And over time, it will gradually rise. And when it rises, typically 1 milligram kWs per gram over its initial starting value, you need to place a watch on that and think about changing the fluid. But the other thing that happens is that as the PAG reaches its end of life, you can see a very dramatic viscosity drop. So if you're condition monitoring lubricant and just looking at viscosity, product will look very, very stable for long periods. But at the end of life, you will see this big drop. That's unlike hydrocarbon oils. The message I want to give you, and perhaps, the listeners to this, is that always track the TAN value, the acid number value, when you're looking at the condition monitoring program. So that's a potential Achilles heel of these types of products. Most organizations do have very good condition monitoring programs. And of course, measuring the TAN value is part of that.
Yeah, interesting. So the only other question I'd have really on sort of the varnish issue, I guess, is you know, the industry seems to be using the term varnish, and this goes back to a previous episode, as a kind of an umbrella term for not only that sort of golden lacquer material that we traditionally see on bearings, but more of an umbrella term for just generally deposits, whether that's sludge or varnish or anything. Um, I've seen a couple of pictures of kind of like a black, it almost looks like glass. I can't really explain it, which was the result of the breakdown of PAGs in gas turbines. What's that behavior? Have you come across that before?
I've come across one or two cases where there have been some issues in gas turbines. Rafe, I think what is going on there, when you do the root cause analysis, it may be that there is a significant thermal event going on in the turbine. And it's not oxidative degradation that is happening. It may be simple thermal degradation. So the two are very different.
Mm.
So that the hot spot in the turbine, um, in that part of the turbine, maybe it's starved of oxygen. So therefore oxidative degradation can't occur. What happens when you get thermal degradation is you get the development of carbon-rich deposits occurring. It's a rare thing to happen, but it's usually a thermal event that has caused that.
Yeah, interesting. Okay, that's good to know. One of the other things that which I think is sort of a feature, I guess, of the PAGs is their tendency to take on a lot of water, right? So people always find that, in condition monitoring programs, the typical water values that they see for PAGs are substantially higher than they would see for other lubricants, mainly because it's reasonably hygroscopic. I always get that word wrong. It seems to pull a bit of water from the atmosphere. My understanding is always that higher levels of water in PAGs are relatively fine, that they seem quite inert to the presence of water. I think people get a little bit freaked out because they always think of esters and the fact that, you expose an ester to water and it's going to fall apart. So, is there any kind of upper threshold that people need to worry about in terms of water contamination?
That's a great question. So PAGs are more tolerant to water and they are hygroscopic. Some types of PAGs can absorb 5 or even 10,000 ppm of water. What is very interesting about PAGs is very often that water is inert. It's held within the polymer matrix. So the PAG is acting like a polymeric sponge for that water, rendering it inert. And so you'll find that many lubricants based on PAGs can operate at much higher water levels. So for example, it's very common to see air compressor lubricants based on PAGs running at levels of 2 to 4,000 ppm of water, as they're exposed to different humidities and so on. And also the seasonal variation from winter to summer through the humidity. So those types of PAGs work extremely well. I take your point on esters. Whenever you have a lot of water and a catalyst, esters are prone to hydrolysis. And I think in applications where there is water ingress into the lubricant, esters are perhaps not the right choice as a synthetic for most applications.
Yeah, cool. Maybe just the last sort of feature, if you like, of the PAGs, just to touch on, would be the biodegradability aspect as well. So I don't know if that's common to all of the PAGs, but certainly some of them are advertised as being biodegradable. Um, how does that happen?
Great question. So what is interesting about PAGs is that typically the lower molecular weight PAGs, so I would say molecular weight less than 1,500 grams per mole, which is around about an ISO 150 viscosity grade. Anything less than that, they have some degree of biodegradability. When you get to ISO 32, ISO 46, many of the PAGs are readily biodegradable. It means that they're very useful for developing products for environmentally sensitive applications where you need high biodegradability. So that's a good point. But the other good point raised on all this is that sometimes you need PAGs to be bioresistant. And particularly in, for example, water-based metalworking fluids, you don't want the microbials in the fluid to destroy the PAG and so on. So what is fascinating about PAGs is that you can design them to be either bioresistant or you can design them to be readily biodegradable by changing that polymer architecture that we talked about a few minutes ago. So they are a good choice for developing environmentally acceptable lubricants.
Interesting. That's really cool. We've already talked a little bit about some applications where PAGs are well suited, right? Such as turbines. Um, we haven't touched on it, but obviously very common in worm drive gearboxes as well. In all of those applications, it feels like people have turned to PAGs to solve a problem that is present in standard hydrocarbon oils, right? So with worm gear drives, it's the fact that we can't use EP additives because of the yellow metals. In compression, it was because they were seeing some varnish issues. In turbines, same thing. In gas compression, we often use PAGs because of the lower solubility with methane and propane. So we're always solving a problem with standard hydrocarbons, and we solve the problem with PAGs. But if you could wipe the slate clean, are there any, and cost wasn't an issue, are there any applications where you think, oh, PAGs would actually really suit this application if everyone wasn't already using hydrocarbon base oils?
Yeah, that's another really good question. I think there are some applications like wind turbine gearboxes where I think PAGs could have a future. I know in my former company, we ran some trials on PAG-based um, wind turbine gearboxes, and the trial was fantastic over a 10-year period. So that is of course one area where you would look at PAGs. I think as we look into the future, though, whenever we think about energy efficiency, which is a big part of sustainability, I think the formulators should have in mind PAGs as a primary base fluid for developing future formulations. And I think as well, Rafe, as we look at the equipment builders and how they're building equipment to be smaller with higher power densities, with high thermal stresses and so on, hydrocarbon might not be suited for certain types of equipment of the future because of the degradation of products, forming deposits and varnish and so on. And so PAGs may be a potential solution to some of those challenges that we might see in the future. So those are some of my thoughts with regards to the future and where PAGs might find a place going forward.
Yeah, that's really interesting. With PAGs, it seems like there's a pretty bright future. Um, I feel like in the turbine space, at least in power generation, there are more people that are sort of receptive to the idea. And again, that's solving the varnish problem in some ways, not solving completely, but certainly helping. Um, is there anything else that's happening in terms of innovation with PAGs? One of the things that you've described is that they're very customizable, right? So you can create effectively an infinite number of different types of PAGs. So is there anything going on in that space that we should be looking for in the future?
Yeah, sure. So when I look at innovation with the PAG manufacturers today, Rafe, I think it feels like it's gone a little bit quiet. And you can measure that through the intellectual property that's being published. You can measure it through conference presentations and research publications and so on. So for whatever reason, so PAG manufacturers have slowed down their innovation programs. But what has happened is that some of the smaller innovative companies are now looking to the future and bringing out new types of technologies. And, there's one company that I'm supporting at the moment, which is the base oil company that bringing to market some new synthetic base oil technology that we describe as secondary polyolesters, but in fact, these materials are what I would consider to be hybrid structures. They have all the features of PAGs and all the environmental characteristics of esters, good biodegradability, produced from renewable feedstocks. You've almost got a hybrid bio-based PAG in some instances. So when we think about sustainability, when we think about developing PAGs of the future, or indeed lubricants of the future based on new synthetic base fluids, this type of science and technology, this type of innovation, I think has a place in our world, building on that 75 years of experience of using PAGs in equipment and so on. So those are kind of my thoughts with regards to innovation and, moving forward.
That's really interesting. Just on that hybrid PAG, which you described as sort of being somewhat polyester, somewhat PAG, do you mind if I just ask, what does that look like? So when we think polyol ester, most people thinking it's that sort of that MPG or TMP core, and you've effectively just got a long hydrocarbon chain that extends off those, depending on how many functional groups you have in the center. So when you describe that hybrid, are you talking about something which looks like an ester at the core, but the arms, so to speak, look like PAGs?
Yeah, let me try and answer that question without giving too much away, Rafe. But may want to take a look at an article just published in Lube magazine, so the February edition of Lube magazine, which
I'll link that.
describes these these types of new hybrid esters. But when we think of polyol esters, we often think of TMP-based esters, pentoerythritol, neopentoglycol type esters, and they serve a really important part of our lubricants industry today. But think of polyols as being a much broader type of precursor for making ester products. And so I think I know where you're going on this. If you think of polyols being essentially PAG-based type precursors, then combining those with some of the ester characteristics, so building ester functionality within those types of materials, leads to these hybrid structures that have all the properties of PAG, such as very high VI, good hydrolytic stability, a great traction behavior, but all the environmental aspects of esters, like I said, high biodegradability, high renewable carbon content, and so on. So this may be where the future is for Group 5 synthetic base oils. And we're excited at the V-Base Oil Company to be able to share this knowledge with the entire lubricants community over the coming months and years.
Yeah, that sounds like a great combination of technologies, because I guess one of the things that plant-based lubricants have always faced, and not necessarily a criticism of them, but the idea is that how are you going to replace the volume, the sheer volume of petroleum-based lubricants? But if you're creating a molecule that's going to last a lot longer than a lot of the mineral oil bases, then obviously the volumes that you require are far less. And so that's kind of a cycle, or whatever you want to call it. So it sounds like a really exciting technology, and I look forward to a lot of the new developments. Well, Martin, hey, really, really appreciate the time that you've given us here today. Hopefully, a lot of people out there have learnt a little bit more about PAGs, and people are generally scared of technologies because they don't know enough about them. And so hopefully this has given people a window into what PAGs are all about, and given them some really good information, particularly on the condition monitoring side. I really like that tip about the viscosity reduction. That's absolutely something to look out for. So hopefully people can take away a few lessons for their specific programs. And yeah, don't be scared of PAGs, I guess is the ultimate answer. But Martin, really appreciate your time, and thank you so much. And I'll have to get you on another time.
Hey, Rafe, it's a real pleasure talking to you today, and I keep doing all that great work on providing these education sessions because I learn a huge amount from these. So it's much appreciated that you've invited me today, and I look forward to chatting with you in the future.
Thank you.